Welcome to the fourth video in quantifying angular motion of a rotating object. So this one will be focusing on a situation where angular acceleration is constant. So if you remember, angular acceleration is the rate at which angular velocity is changing. So it just to look at constant angular acceleration means constant means if it is the direction of angular acceleration is same, meaning say if I have a situation in which at some instant ti the marker is this way and is going at omega I, and some other instant marker is here, tf, marker is here, and the speed at that point is omega f. Then between here and here, either is alpha is positive, alpha is negative. So constant angular acceleration, what does it mean? It means during ti to tf, direction of alpha is fixed. So that means it can be either clockwise sense or counterclockwise sense. So whatever it is fixed. For instance, over here, if the axis was pointed this way, this is the axis, and I'm looking from the axis, so this will be if it's speeding up, then alpha will be positive. If it's slowing down, then alpha will point down below here, so alpha will be negative. So that means either alpha is positive or alpha is negative. Okay, so but it's not like it's positive over here and the negative over here. It's between entire time, it's been either all the time positive or all the time negative. Okay, so that's what it means, direction to be fixed. So that's one thing. And second is the magnitude of alpha is fixed. That means if this was 5 radian per second squared, it's 5 throughout. So this is what it means. Okay, we're going to denote this by putting a symbol on it, so it's like bar. So we'll read it alpha bar, just to make sure that we understand the limitations of these equations. So where the equations come in is going to be like this. So we are going to examine between here and here, between two instants ti to tf, what are the different relationships. So if this is fixed, so number one relationship we're going to get is, if fixed, then the average change, rate of change is the same as the fixed one. So this makes is no-brainer, right? So this is the change in angular velocity, and it took, we're going to indicate delta t is tf minus ti, just for simplicity. So delta t, so this is the average angular acceleration, which has to be the same as the constant one. So that's one equation. You can write it many different ways. You can write omega f, omega I mean, equals omega I plus alpha bar delta t. You can write like that. But this is basically coming from conceptual definition. Okay, another thing that happens is how much angle it has rotated. Well, it might have. You might have gone from here to here, or it might have gone whatever many times, but in it appears. So it's total angle that is rotated. So this is not just the direction, but the total angle rotated. So let's see, delta theta is total angle rotated. So if I look at this over this, that's going to be the average angular velocity, right? So delta theta or delta t will give me average angular speed, so to say. Well, if I have this is the speed now, and this will be the speed later, then if I add these two guys, that will be also omega I plus omega f over 2 will also give average angular speed if alpha constant. See, if it's changing steadily to that, this angular speed changing to that angular speed, then the average will also be like that. So equating these two will give me the second equation. The second equation is delta theta over delta t is omega I plus omega f over 2. So you can write this another way. You can write omega, omega I plus omega f is equal to 2 times delta theta over delta t, or you can write down as delta theta equals omega I plus omega f over 2. That's the average guy times delta t. So a whole bunch of different ways of writing it, right? But this makes perfect sense, and this makes perfect sense conceptually. And I kind of try to remember this way. The other ways of writing, there's only two relations, but you can eliminate delta t from these two guys, and you can get omega f square equals omega I square plus 2 times alpha bar times delta theta. So this is kind of no delta t equation. So if there's a problem in which I don't need to find delta t, I can just use this directly. You can, but all of them seem to have omega f, and I could actually eliminate omega f from these two guys instead of delta t, omega f. Well, that will give me delta theta equals omega I delta t plus half alpha bar delta t squared. So this is no omega f equation. And turns out these two guys come from these two, but they are very powerful. They are very useful, very, very, very useful in solving problems. So let's apply them in a situation and see numerical problem and how they will work out. So we are going to apply to an example of a centrifuge, say speeding a centrifuge to its maximum angular speed of, say this centrifuge has 20,000 RPM. What is RPM? Revolution per minute. I want to speed it in say I want to get all the way up there in 2 minutes. Okay, so what kinds of what kinds of alpha I will need. And if you look at this, if I start with 0, so I've been given this, I have been given this, I have been given this, so I can find this, and I find delta theta. So I actually, so two things I can find it: how many spins, how many revolutions to get to final speed, right? So I can ask these questions. You may keep everything in RPM. You don't have to change units, radian, etc. You can use the unit of minute. You can keep everything in minute or second. So as long as you have consistent units, those formulas all work. So there's no need to convert all to some other kind of unit, all right? So let's see. So how I'm going to get, first of all, notice that behind the scene, I have not been given, but the way the problem is misstated, there is a thing called starting. How do it get started? Starting from rest. So that's kind of hidden information often in problems. You have to read it. So omega I is 0. Omega F is 20,000 RPM. Delta T is 2 minutes. So these are same units. I don't need to convert. So if I look at alpha bar, is going to be omega F minus omega I over delta T, and it's going to have a 20,000 RPM minus 0 over 2 minutes. So I'm going to get 10,000 revolution divided by minute squares. This is a kind of weird unit, but if you don't like it, you could, I'm not going to do it, you could convert to radian per second square. Maybe try it, it's good practice, okay? So this I got this done. I asked alpha, but I got alpha bar because I'm assuming constant acceleration. So that's it. How many revolutions? This is about, I can find delta theta. Now because I'm doing the revolution unit, I'm going to get answer directly into revolution, not going to get in radian, and so I don't need to any convert. So delta theta is omega I delta t plus half alpha bar delta t square. So I already know delta t, this is 0, and so this, I just figured out alpha bar, so half times 10,000 revolution plus divided by minute square times 2 minute square is 4, 2 minute square is 4 minute squares, so minute square cancel out. You can see this unit emerging right away. So this is 2 with 2, so this is 20,000. This is interesting set of numbers. Actually, it takes 20,000 revolutions to get to 20,000 revolutions per minute. That's interesting. Just worked out numerically like this. Now, you can say, hey, will it always get this? That's a good question. I'm always going to get this. How about if I had started with 10,000 here? Will I get this? I would say, see if you can answer your questions like that. What if it took me 5 minutes to do it, to get there? Will I still be getting that RPM? So let's see if I'm going to just cross things out here. In my calculation, say this was 5 minutes, what will happen? This 5 minutes. So this I'll get at 5 minutes. And so this will be 4,000. And so this will be 4,000. And at 5 minutes, 5 minutes will be, so leave it 2 alone. And 5 minutes will be 25 minutes squared. So if I had 2 with 2,000. So when I multiply with this, I have a 50,000 RPM revolutions. So to get to that, the original answer was just fortuitous. It's just happened to be those numbers work out nicely. So when you look at it, Don't try to see I'm gonna guess it the same. You have to work through it, and then you will get the number, correct number. I'm gonna stop here. These 4 or so videos completes our discussion of the what is called kinematics, kinematics of rotation. Rotation is a very long chapter. The next we're going to talk about dynamics, and dynamics will involve moment of inertia, torque, angular momentum, and we will have a second law for rotation. So that all of these things are coming up. Let's stop here. You can study these things. Take care. Bye.